In the previous video, we saw how to construct a new series from an existing series, and this was done by grouping. In this video, we will see another process. This is called as rearrangement. As the name suggests, all we are doing is rearranging the terms in the series to get a new series. Let us try to give a rigorous definition for this. We say a series Yn is a rearrangement of a series Xn if there is a bijection f from n to n such that yk is equal to x f of k for all k in n. Let us see some examples. So we will take the harmonic series, which is 1 plus half plus 1 by 3 plus 1 by 4 plus 1 by 5 plus 1 by 6 plus etc. And then we will rearrange this. One possible rearrangement is we will swap half and 1, then we will swap 1/3 and 1/4, then we will swap 1/5 and 1/6, etc. So we will just pair it into groups of 2, and in each group of 2 we are swapping it. That is one rearrangement of the harmonic series. Another rearrangement is the following. We will take one odd term, then 2 even terms, then one odd term, then 2 even terms, etc. So you will get 1 plus half plus 1 by 4th plus 1/3 plus 1/6 plus 1 by 8 plus 1 by 5 plus 1 by 10 plus 1 by 12 plus 1 by 7 plus etc. So this is also a rearrangement. There are so many other ways we can rearrange the harmonic series, but I will let you play with that. Now we will prove that if you have an absolutely convergent series, then any rearrangement will also converge to the same value. So let Xn be and some series Xn be absolutely convergent. Then any rearrangement let's call the rearrangement Yn of Xn converges to the same value. Proof. So let summation Xn, the value be x, and let Sn be x1 plus x2 plus etc. up to xn. So we know series Xn converges. Because series Xn converges, Sn also converges. And series Xn converges, it means that this series, which is equal to k going from n to infinity of Xn, also converges. Let us give a name for this series, this special series. We will call it capital T of n to stand for tail of the series. So that's why it's the nth tail. Okay. So we know that the partial sums are getting closer and closer to the total value of the series. So because of that, the tail has to get smaller and smaller, and hence Tn has to converge to 0 as n tends to infinity. Because of these two facts, that is Sn converges to x and Tn converges to 0, we can, given any epsilon greater than 0, there exists an n which depends on epsilon, a natural number, such that mod of Sn minus x is less than epsilon and mod of Tn minus 0 is less than epsilon for all n greater than n of epsilon. We can find an n of epsilon such that both these inequalities are satisfied. That's what we are saying. Now let m be such that x1 etc. up to xn are contained in Tm, which is equal to y1 plus etc. up to y capital M. If M is greater than capital M and N is greater than N of epsilon, then if you look at the difference Tm minus Sn, so this will have finitely many terms xn where n is greater than n of epsilon. So mod of Tn minus Sn would be less than or equal to summation of x k, where k is going from n of epsilon plus 1 to infinity. Now we know that this quantity is less than epsilon. Why is this quantity less than epsilon? Because we have chosen n of epsilon such that Tn is less than epsilon, and this quantity that we have right here is nothing but Tn of epsilon. N of epsilon plus 1. So because of that, that has to be less than epsilon. So what have we proved so far? We have proved that mod of Tm minus Sn is less than epsilon. We can make this small enough by making Mn large. And we also know that mod of Sn minus x is less than epsilon, where even n is large. So we combine these two things using our usual triangle inequality trick to show that mod of Tm minus x is also less than epsilon. Okay, so mod of Tm minus x is equal to mod of Tm minus Sn plus Sn minus x, which by triangle inequality is less than or equal to Tm minus Sn plus mod Sn minus x. Now each of these quantities is less than or equal to epsilon when n and m are large. That's what we have shown earlier. So because of that, we know that the sum can be made less than or equal to 2 epsilon. So we can make Tm minus x arbitrarily small, and hence Tm converges to x. So because Tm converges to x, we get that the series yk converges to x. That's the end of the proof. We saw that if a series is absolutely convergent, then any rearrangement converges and has the same value. Now the question is, what happens if the series was conditionally convergent? That is, it is convergent but not absolutely convergent. In this case, we will show that we can find a rearrangement such that it will converge to any value you want. More precisely, if you give me a value, I will construct a rearrangement such that the rearranged sequence will converge to the value you had given me. Let us go through the statement of the theorem once more. If series xn is conditionally convergent, then given any real number s, we can find a rearrangement yn of xn such that the series yn has value s. Let me give a brief sketch of the proof before actually jumping into the proof of the theorem. So what we will do is the following. We will collect all the positive terms of the series xn, collect all the negative terms of the series xn, and form two new series out of the series xn. What we will show is that the series of positive terms and series of negative terms both will have to diverge. So given this fact that both the series of positive terms and series of negative terms diverge, how will we prove that we can make it converge to any chosen value? First, add just enough terms from the positive series, a finite sum, such that the finite sum is greater than the chosen value. Then we will add just enough number of terms from the negative series to make it less than the chosen value. Repeat. We again add in just enough number of points from the positive series to make it greater than the chosen value. again add enough number from the negative series to make it slightly less than the chosen value, etc. So at each stage, we have like it overshoots, right? Either it overshoots or like goes below, undershoots, overshoots or undershoots. The idea is that at each iterative step, the amount by which it undershoots or overshoots keeps decreasing. Why is this the case? This is because the value of xn is converging to 0. For any convergent series, we know that xn has to converge to 0. So we are adding smaller and smaller quantity. Because of this, the amount by which it overshoots or undershoots has to decrease, and hence it will eventually converge it to the chosen value. This is the idea of the proof. Now let us go through the proof a little more rigorously. We construct two new sequences called xn plus and xn minus, where xn plus is equal to xn if xn is greater than 0 and 0 otherwise, and xn minus is equal to xn if xn is less than 0 and 0 otherwise. Notice that xn is equal to xn plus xn minus. Notice here we can look at series xn plus as the series of positive terms and series xn minus as the series of negative terms. So that is why we have defined something like this. We claim that both the series xn plus and xn minus diverges. How do we prove this? The basic proof strategy is proof by exhaustion. We will consider all cases and show that except for the case where series xn plus and series xn minus are divergent, the other cases lead to a contradiction. That's what we will show. First, let us look at case 1, which is series xn plus and series xn minus are convergent. So, to do this, we have to first look at a homework problem. The homework problem is show that if xn is greater than or equal to 0 and similarly xn is less than or equal to 0, then series xn is absolutely convergent if and only if series xn is convergent. So because of this homework problem, we will get that if xn plus and xn minus are convergent, then they will both be absolutely convergent. But we can show that if series xn and series yn are absolutely convergent, then series xn plus yn is absolutely convergent. So let's go through it again. Homework 1 implies that xn plus and xn minus are absolutely convergent. And this fact along with homework 2 implies that xn plus xn minus is absolutely convergent. It implies that xn is absolutely convergent, which contradicts the assumption that series xn is conditionally convergent. So case 1 is impossible. Let us now look at case 2. Case 2 is series xn plus is divergent, but series xn minus is convergent. Okay, we will again show this is impossible by showing that this will imply that xn does not converge. So that is the contradiction we will arrive at. For convenience, we will introduce some notation. So Sn plus will denote the partial sums for xn plus. which is nothing but x1 plus etc. up to xn plus. Similarly, Sn minus will denote the partial sums for xn minus, which will be equal to x1 minus plus etc. up to xn minus. What can we conclude from the fact that series xn minus is convergent? It means that the sequence Sn minus is convergent, but Sn minus is a strictly decreasing function, so it is convergent if and only if it is bounded below. So because of this, what we can say is, we can say that Sn minus is greater than or equal to minus m for some positive number m. On the other hand, as series xn plus is divergent, Sn plus is divergent. Also notice that Sn plus is an increasing sequence. Because it's an increasing sequence, it's divergent if and only if it is not bounded. So this will imply that Sn plus is not bounded. What do we mean by it is not bounded? What we have is, given any A, there exists an n that depends on A such that Sn plus is greater than A plus m for all n greater than or equal to n of A. But from these two inequalities, we get that Sn plus Sn minus is greater than or equal to A plus m minus m, which is equal to A. But Sn plus Sn minus is equal to Sn. So Sn is greater than or equal to A. And A was arbitrary. So you can make Sn as large as you want. The partial sums for xn can be, the series xn can be made as large as you want, which will imply that the series xn has to diverge, which is a contradiction. Okay, so this implies that series xn diverges, which is a contradiction. So case 2 is also not possible. What is case 3? Case 3 is series xn plus is convergent, but series xn minus is divergent. This again is not possible. You can again conclude that this will imply that series xn has to diverge, and the argument is very similar to case 2. So I leave the proof of this case as a homework. As we proved that case 1, case 2 and case 3 are impossible, the only possibility is case 4. So case 4 has to be true, and case 4 was nothing but xn plus diverges and xn minus diverges. As this is the only case left, this has to be true. Thus, we have proved our claim that series xn plus and series xn minus will diverge. So we have showed that both the series of positive terms and series of negative terms will diverge, and we will use this to construct a rearrangement which will converge to a chosen value. Let's call that m. So let's try to prove this rigorously. We know that summation xn plus diverges, so we can find a p such that summation of xn plus from 1 to p is greater than m. Remember, we had mentioned earlier that we want to choose the smallest p such that this happens. So to make that precise, what we do is we want n going from 1 to p minus 1 of xn plus to be less than or equal to m. So this is the first time when this is greater than m. This already gives us some clue as to how we should rearrange the series. What we basically are doing is we have to discard all the zero terms. So for example, we can define f of 1 to be the minimum minimum of all n such that xn plus is not equal to 0 and 1 less than or equal to n less than or equal to p. Similarly, f2 is equal to minimum of all n such that xn plus is not equal to 0 and f of 1 is strictly less than n is less than or equal to p. Now, if you are given f of k, we can define the general f of k plus 1 as follows. It is the minimum of all n such that xn plus is not equal to 0 and f of k is less than n is less than or equal to p. Of course, this is not an infinite process, but it's a finite process because at max we can find finite p many points, right? But we might end up before this because the number of non-zero terms that among x1, x1 plus, x2 plus, etc. up to xp plus might be less than p. So we might stop before p. But we still have the function f defined till some stage at this point itself. We can let's say that we have defined it till f of m1. Now because an minus 1 also converges, we can add enough terms to make it smaller than m. So what do we want? We want summation of n going from 1 to p of xn plus summation of n going from 1 to q of xn minus should be strictly less than m. That's what we want. But we also want, as before, this to be the smallest q for which this happens. How do we make that precise? The smallest such q would be the q for which m is less than or equal to summation of n going from 1 to p of xn plus summation of n going from 1 to q minus 1 of xn minus. This allows us to extend f further. For example, we can define f of m1 plus 1 to be the smallest n such that xn minus is not equal to 0 and 1 less than or equal to n less than or equal to q. F of m1 plus 2 is equal to minimum of n such that xn minus is not equal to 0 and f of m1 plus 1 is strictly less than n is less than or equal to q. Finally, if we know f of m1 plus k, we can define f of m1 plus k plus 1 as minimum of n such that xn minus 1 is not equal to 0 and f m1 plus k is less than n is less than or equal to q. So we have again defined f from m1 plus 1 to f of m2 for some m2. And we keep on doing this process. We overshoot, then undershoot, overshoot, then undershoot, overshoot and undershoot. And by this process, we can define the function f from n to m. As already mentioned before, the amount by which we overshoot and undershoot will keep decreasing because the sequence xn is converging to 0. So because of that, the series x f of n converges to m. And that is the end of the proof.